Hello all. So today we will talk about exercise 8.47, the spool. It is about the spool of mass m with moment inertia I, and it's free to roll without slipping on a table. And so straight away we know that there's a friction acting here because otherwise if there's no friction this spool wouldn't start to rotate. And it has an inner radius r and an outer radius capital R. And then we're pulling it on the string with tension T, which looks like this. And it forms an angle theta with the horizontal. And it is asking us for the acceleration of the spool and which way it moves, depending on theta. So whenever we encounter a mechanics problem like this, it is never wrong to try to lay out the formula for the torque and for the force. So let's try force first. For force, we can go down two paths. We can either lay out the x direction or the y direction, that force expression. Now, y direction wouldn't be as useful because the formula would just be t sine theta is smaller or equal to mg, since we assume that the spool wouldn't lift off the table because of this tension force. And so that is sort of the only formula, or we can also include the normal force in there, but it is not useful. It is not as useful in finding the acceleration because there's no acceleration in the y direction. And so let's try the x direction for f net. So for x direction, we have t cosine theta minus f equals to ma. And take note here of the sign convention. This is very important. So here we define right acceleration as positive. And this is very important when we list out the formula for the net torque. So right now here we have the net force in the x direction formula. Now for the net torque, we have t times small r minus f times big R equals to I alpha. And take note here, this is wrong. We need to flip the signs. It should be Fr minus Tr equals to I alpha. Why? Because imagine a sphere. If we define the right direction, the linear right direction, as positive, then doesn't that mean the clockwise angular acceleration is also positive? And so then if we look at a diagram here, it is the friction that is bringing a clockwise acceleration, and it is the tension that is bringing an anti-clockwise. And so that is why TR is negative and FR is positive. And so that is why sign convention is really important here. Otherwise, we would have gotten the opposite result. And so now let's just sub in and solve the system of formulas, since we just have two unknowns. We can do this. And also for alpha, we can also relate it by the formula alpha capital R equals to A. And so three formulas, three unknowns, the system is fully solvable. So let's try to do that. So friction equals to MA, or friction equals to T cosine theta minus MA. And so let's sub in that formula back to here. We have T cosine theta, or TR cosine theta, minus MAR minus TR equals to I alpha. And remember, I alpha can be written as IA over R. And so since we're trying to find A here, let's move this to that part and we can separate out the terms. So first let's try to factorize this. So we have T R cosine theta minus R equals to I alpha. And now we move this to the right side. We have I A over R plus MAR. And now we can factor out this A term, which we have T R cosine theta minus R equals to A I over R plus MR. And so A equals to T R cosine theta minus R over I over R plus MR. And so that is our final answer to this question. And then the question always also asks us which way it moves. So if we pay attention to the expression here, the only quantity that can be negative here is this. Because tension, we're just assuming we're pulling it along the string. No one's going to push the string. and so tension will always be positive. And obviously, moment of inertia and radius will always be positive, and the same goes with mass, and so it is always positive. And so the sole determiner of whether this A is positive or negative is r cosine theta minus r. And so let's set that to 0 and see what happens. So we have cosine theta equals to r over r. And so this is the most important result, because here, if cosine theta is bigger than r over r, small r over capital R, then we know that this expression will always come out. We know that capital R cosine theta minus r will always be positive. If it's the reverse, cosine theta is smaller to small r over capital R, we know that the acceleration is always negative. And if they are equal, we know that there is no linear acceleration. So it's 0. And so that is our answer to this exercise. Thank you for watching.